Okay, so we have an applied functional analysis practice final exam at the graduate level. This is part one. So let's begin. So number one, we have let x comma d be a metric space, and we want to define c sub b of x, given that x r, f is continuous and bounded with this metric, d infinity of fg, and the supremum metric here, the largest difference between the two functions, f of x and g of x. Okay, part A, B, C, D show that d infinity defines a metric on c sub b of x. Let f sub n be a Cauchy sequence in this c sub b of x d infinity. Show that there exists a bounded function such that such that f sub n goes to f uniformly on x, and prove that f is continuous. Conclude that c sub b of x comma d infinity is complete. So metric spaces and completeness problem. So for part A, we're going to employ the metric property, and since fg are bounded, f minus g is bounded, so the supremum is finite. So we're going to verify the metric axioms. So first, d infinity fg, that's greater than or equal to 0 because absolute values are non-negative. Second, d infinity fg equals 0, and that means the supremum, that difference between f of x and g of x, the largest difference, that equals 0. And therefore, that absolute value of f of x minus g of x equals 0 for every x in x. So f of x equals g of x for all x. Okay, so for x being an element of x, if you want to say it that way, and hence f equals g. So third, d infinity f comma g, that's going to equal this sup of absolute value f of x minus g of x equals sup of x, that g of x minus f of x, absolute value of that equals d infinity g comma f. And fourth, for any fgh, this difference here, f of x minus g of x, absolute value of that is less than or equal to the absolute value of f of x minus g of x plus the absolute value of g of x minus h of x. And taking the suprema gives d sub infinity f comma h is less than d infinity f comma g plus d infinity g comma h. So that's that d infinity is a metric. So that's part A, and on the second page, we're going to go on to B, C, and D. Okay, so let's move along to B, C, and D. Oops, sorry. That. So, old-fashioned setup here. Okay, so uniform limit exists. Let f sub n be Cauchy to n d infinity. Then for every epsilon greater than 0, there exists n such that if m, lowercase n is greater than or equal to capital N, and then we have the supremum again, x, an element of capital X, that f sub n of x minus f sub m of x, absolute value of that less than epsilon. Hence, for each fixed x being an element of capital X, we have the absolute value of this difference between f of sub n of x minus f of sub m of x is less than epsilon. So f sub n of x is a Cauchy sequence in R space. And since R space is complete, define f of x equals limit as n approaches infinity, f sub n of x. We're going to fix epsilon greater than 0. Choose n so that for m comma n is greater than or equal to n. And this absolute value here of f sub n of x minus f sub n of x, f sub m of x is less than epsilon for all x. Letting m go to infinity or approach infinity, we get absolute value of f sub n of x minus f of x is less than or equal to epsilon for all x. Therefore, okay, we get this norm here, this f sub n minus f norm infinity, okay, is less or equal to epsilon. So f sub n, that's going to go to f uniformly. Okay. All right. Letter C, continuity of f. Each f sub n is continuous. F sub n arrow f uniformly to show f is continuous, fix x naught is in capital is an element of capital X and epsilon greater than 0. Choose n such that that norm f minus f sub n infinity is less than epsilon over 3. Since f sub n is continuous at x naught, there exists delta greater than 0. My apologies for that delta being poorly drawn. Such that if d of x, comma, x naught less than delta sub 1, okay, then, I'm sorry, less than delta, my apologies, then this absolute value of f sub n of x minus f sub n of x naught, that's less than epsilon over 3. Moving forward in this chain reaction, then we could say absolute value, if you want to call it a chain reaction, just the way the information flows, absolute value of f of x minus f of x naught less than or equal to absolute value of f of x minus f sub n of x plus the absolute value of the difference between f sub n x and f sub n x naught plus the difference between the absolute value of f sub n x naught and f sub f x naught. Okay, a lot of words. So each term is less than epsilon over 3. Okay? And so this absolute value of f of x minus f of x naught is less than epsilon. So you can say f is continuous. All right, and in regards to completeness, every Cauchy sequence in C sub b of x converges uniformly to a continuous function f as shown. Also, f is bounded because for some n, this norm f minus f sub n infinity is less than 1, and f sub n is bounded. Hence, that absolute value of f of x is less than or equal to absolute value of f sub n of x less than 1. And f sub n is bounded. Hence, absolute value of f of x is less than or equal to absolute value of f sub n of x plus 1. So, f is an element of C sub b of x. Therefore, C sub b of x is complete. Okay, so that's number 1. Let's move along now to number 2. Okay, so number 2. Okay, let this x equal c of 0, 1, and equipped with the following here. We have that norm f sub infinity, or f norm infinity, as some would call it, equals that max there, maximum over x in 0, 1, that absolute value of f of x, and we're going to define this t applied to f at x for this integral. It's set equal to the integral 0 to x e to the negative quantity x minus s f of s ds. Okay, so a, b, c, d, e are shown here respectively. So show that that t x arrow x is linear, show that t is bounded, compute an upper bound for that t norm, determine whether t is compact, interpret T as a solution operator for an ordinary differential equation. Okay, so this is a Banach space of continuous functions. So we're going to let x equal that C 0, 1, and equipped with that norm, f norm infinity, and that equals that max, x being an element in that 0, 1 interval, absolute value f of x. We're going to define that t applied to f of x equals this integral given. And for a, the linearity for fg is going to be an element of that c, 0, 1, and scalars alpha, beta. That t now here applied, okay, now to this x, but we have this alpha f plus alpha b of alpha f plus beta g of x. All right, so that t being applied to that, and that equals that integral 0 to x e to the negative quantity x minus s times this quantity alpha f of s plus beta g of s dx. Okay, so integrated in terms of s there. So by linearity of the integral, and that's a single variable integral. Okay, by linearity of the integral, we're going to get that this t applied to x here of these quantities applied to x equals that alpha t to t applied to f at x. Okay, that's going to equal this. Sorry about the background noise. It's going to equal this quantity t. Okay, applied to f at x plus that beta t applied to g at x. So t is linear. Sorry about that. There was some noise in the background. B, boundedness. Okay, show that t is bounded. So since f is an element in that C, 0, 1, that magnitude or absolute value of f of s is less than or equal to that f norm infinity. So again, we're going to have this absolute value here of a t applied to f at x is less than or equal to this integral, 0 to x e to the negative quantity x minus minus s, absolute value of f of s ds. That's going to be less than or equal to that f norm infinity. And then the integral 0 to x e to the negative quantity x minus s ds. And some of the steps are left out with the computation. If we calculate the integral from 0 to x here, we're going to get 1 minus e to the negative x. So that absolute value of t applied to f at x, that's less than or equal to quantity 1 minus e to the negative x, f norm infinity. And since 0 is less than or equal to x is less than or equal to 1, okay, so we have this, since 0 is less than or equal to x is less than or equal to 1, 1 minus e to the negative x is less than or equal to 1 minus e to the negative 1, or 1 minus 1 over e. So that here, the tf, okay, that norm infinity less than or equal to 1 minus e to the negative 1, f norm infinity, and t is bounded. Okay, so that's for letter B. Now moving on to C, D, and E on the second page. Okay, so here we have second page here. Sorry, so operator norm. Okay, we have that norm t less than or equal to 1 minus e to the negative 1 was shown. And to show equality, we're going to take the following, and then that norm f infinity equals 1, and that t applied to f at x equals 1 minus e to the negative x, thus we get the following. This equal to 1 minus e to the negative 1, and therefore that norm t equals 1 minus e to the negative 1. Okay, for letter D, we're determining whether t is compact. So compactness, so we're going to let that norm, f norm infinity, be less than or equal to 1, and then that t applied to f at x less than or equal to 1 minus e to the negative 1. So the family given is this, tf colon f norm infinity less than or equal to 1 is uniformly bounded, and also that tf prime applied x, that equals f of x minus t f of x. So therefore we could say the following. Okay, this term, this tf prime of x, that magnitude of that, or absolute value, less than or equal to the absolute value of f of x, plus that t applied to f of x, absolute value of that, less than or equal to 1 plus quantity 1 minus e to the negative 1. Okay, so the image of the unit ball is uniformly bounded and equicontinuous, and by Arzella Ascoli, its closure in C01 is compact. And my apologies if I mispronounce the names. I'm not, I've heard them pronounced in an anglicized way, but I'm not a language expert. I don't know the proper way to pronounce a lot of these. At least I've heard it in different forms, but I am not a language expert or anything like that, so I apologize for any mispronunciation of anything. And letter E, ODE interpretation. Okay, this u of x equals that t f applied to x. Then this u of x equals integral 0 to x e to the negative quantity x minus s f of s ds. Differentiating u prime of x equals f of x minus u of x. Also, u of 0 is 0. So therefore, u solves u prime x plus u of x equals f of x, and u of 0 equals 0. So t is a solution operator for this initial value problem. Okay, so moving along to number 3. Okay, in part 1. Okay, so for number 3, we let that C01 beta lambda be the Lebesgue measure space, define f sub n of x equals this n 1/2 this chi 0 1 over n of x. And I've heard this symbol pronounced, some people pronounce it chi, some people pronounce it chi. I've heard it pronounced all different ways, and by professors especially. So the Greek letters, especially, even with phi and phi, you always hear them pronounced in differently for some reason. So show that f sub n approaches a 0 almost everywhere. Okay, compute this norm f sub n, and then that's L1. Compute this norm f sub n, L2. Determine whether f sub n converges strongly in L1. Determine whether f sub n converges strongly in L2. Discuss the relevance of this example in PDE weak solution theory. Okay, so measurable spaces and LP spaces. So we're going to let f sub n of x equal what we were given. And almost everywhere convergence. For this, fix x is greater than 0 for sufficiently large n, 1 over n is less than x. Then x is technically not an element from that 0 to 1 over n. So f sub n of x equals 0. Thus, f sub n x going to 0 for every x greater than 0. At x equals 0, f sub n of 0 equals n to the 1/2. So it does not converge to 0, but that 0 has measure 0. Therefore, f sub n going to 0 almost everywhere, or approaching. Okay. For part B, that L1 norm f sub n L1 0 to equals that integral 0 to 1 absolute value of f sub n of x dx equals 0 to 1 over n to the 1/2 dx. So f sub n norm L sub 1, that's going to equal n to the 1/2 times 1 over n equals 1 over square root of n. Okay, so that norm f sub n L1 that is going to 0 or approaching 0. Okay, people again use different terms to show that, or speak about that rather. But that's for letter A and letter B. Letter C. Okay, so C, D, E, and F are on the next page. Okay, so let's see. So for C, that L2 norm, that's going to yield us F sub n norm, that L2 norm, that L2 norm squared, L2 norm squared, and that's going to equal that 0 to 1 f sub n of x, magnitude of that squared dx, and that's going to equal the integral from 0 to 1 over n dx. Thus, that magnitude here, or that norm rather, I should say, sorry, not magnitude, norm L2 squared f sub n equals n times 1 over n equals 1. Therefore, that f sub n there, L2, that norm of it squared, that L2, not squared. So the norm here of f sub n, that L2 equals 1. Okay, so this comes out to 1. Therefore, this comes out to 1 here too. Sorry about that. A lot of background noise. I'm getting thrown off. Sorry. Strong convergence in L1. Since we have this norm f sub n minus 0, that L1 equals 1 over square root of n, going to 0. We have f sub n going to 0, approaching 0, strongly in L1. Strong convergence in L2, since we have this difference in the norm f sub n minus 0, L2 equals 1 for every n. F sub n does not converge strongly to 0 in L2. Okay. And here, PDE, partial differential equation relevance. This example shows that pointwise convergence does not necessarily imply convergence in stronger norms. In PDE theory, sequences of approximate solutions may converge almost everywhere or weakly, while their norms remain bounded away from 0. This matters when passing the limits in nonlinear terms. Okay. So I'm just going to pause it there. That's part 1, 1 through 3, and we'll pick up with the second part. Thank you.